thank you for having me here and thank you for coming to the talk. So some of you might already be familiar with this idea of diffusion models. If you've ever, for example, generated an image here, I do it with ChatGPT. The thing that it uses under the hood is a diffusion model. So it starts with kind of random noise, and then in a few steps, it denoises it into, in this case, I generated Paris in the 1960s. So it takes this random noise and then denoises it into whatever prompt you actually want to get. And more recently, this idea has also been applied to language models. So there's this company, Inception, which is based in San Francisco, and they're basically saying, okay, can we actually try similar ideas, but for language? And if you go to their website, of course, they have a very nice demo. So they show that their model, Mercury 2, is much faster than a regular autoregressive model. And this is partly how they sell this idea that potentially you can get these kind of speed gains. So what I want to talk about is basically to first explain you what are these discrete diffusions. So how can we make this idea that works super, super, super well on images? How could we leverage it for discrete data such as tokens? But at the same time, it's kind of like a more broader question or idea, which is, can we actually do better than the current architectures and the current training methods that we have? So we are very, very good with autoregressive, but are there actually ideas that could push us even further? Are there things autoregressive models cannot do? So there will be some maths in my slides, so I hope you stay with me throughout my mathy slides. But you can ask me questions at the end if anything was not very clear. So a quick recap of what I mean when I say autoregressive models, like what is the core components that these kinds of models are based on. The idea is actually very simple. We are basically modeling our sequence, which I denote as X, as this decomposition on these conditional probabilities. So every element in my sequence is modeled as a probability distribution conditioned on whatever came before it. And so then whenever I train the model, I essentially try to optimize a loss function that would then maximize the probability of the true token that I have in all my pre-training data sets, conditional on whatever came before that token. So everything we do with autoregressive models, it's given this thing, what would be the next thing? I train it such that the next thing is as likely as possible the ground truth that I have. And when I generate, I'm kind of limited to this one by one, token by token generation. So this is an image which maybe makes things more clear. During training, I would take my sequence, let's say x1, x2, x3, x4, and I would train the model to output the ground truth x2, the ground truth x3, and the ground truth x4. And then at inference time, I don't have what happens after x4, but I use the model to generate my x5. I prepend this into my original sequence x5, then I use that to generate x6, and so on. So again, very many words to say the very basic thing, that everything goes one by one, left to right, and everything I'm interested in modeling are these conditional distributions. So how likely is this token given this path that I have input into my model? And if we look at for example, this artificial analysis LLM leaderboards, many of the models that you will see that top these charts, they are these kinds of autoregressive models. So autoregressive models is what we've been putting so much effort into making work, making fast, and so forth. But interestingly, this model Mercury 2, which is this model from these Inception guys, is actually at least entering this leaderboard on the speed element. So there seems to be some competition on this autoregressive one-by-one modeling by this approach that takes this kind of discrete diffusion framework. So again, the same video that I showed you before, but one of the big things that Mercury promotes is really iteration generation speed. Because you're no longer limited from left to right one by one, there are sort of more creative things that you can do. You can denoise multiple tokens at the same time, and I'll say more on how we can actually do this. So basically, this is the big claim that they make. Look, we generate all of this in just 8 iterations, while the transformer, the autoregressive transformer, would take like much longer to get to the same text. Okay, so a few more details on why we would ever kind of look beyond these autoregressive models. The first one is that maybe there are fundamental limits as to what these autoregressive models can do. So we're always limited by generating one by one left to right. And maybe there are certain things that are not possible if we limit ourselves to this framework. And so there was a paper that's called the reversal curse LLMs trained on A is B fail to learn B is A. And what they say is, suppose that we train a model on, for example, this Valentina was the first woman to travel to space. It won't necessarily automatically be able to answer who was the first woman to travel to space. While as a human, I think this equation of if A is B, then it obviously kind of also B is A. That's like a relationship that we know. To the model, it is not as obvious. And if you look in one of the papers on these kinds of discrete diffusions, this is also something that they test, and they kind of claim that discrete diffusions maybe actually do this better. So they might be better at like learning these relationships that don't come as naturally to these autoregressive models. I should say that, of course, it's still possible to teach the model from this sentence to also know who was the first woman to travel to space, but you would require a little bit more training data, because you would also need to show it, oh, if I ask you a question of like who was the first woman to travel to space, and I've given you this fact, Valentina was the first woman, you should answer it like this. So I'm saying this because I'm not saying that autoregressive models couldn't do it. They could, but they would require like specific training. So we would fine-tune them on specifically kind of this style of question answering. Another thing that I heard a lot when already 2 years ago, I was discussing with these folks that did a lot of work on this discrete diffusions back in Stanford. They were saying that large language models potentially could not reliably self-correct. And what they meant by this is if you ask, for example, some kind of like mathematical reasoning problem to a model and it goes off into a direction that is completely wrong, it won't necessarily be able to re-steer itself to a proper output. We've done a lot of work on this. So this is also a paper from 2024 that basically shows the same as I just said, that if you ask the model to rethink, reflect on its own answer, the performance on very many benchmarks actually drops. So if you say, are you actually sure about this? Then the model kind of like, starts making more mistakes. But the reasoning models have done a lot of work to actually be able to do this, because reasoning models rely on exactly this, these kinds of long reasoning trajectories. If you've ever read like the DeepSeek paper, at some point they also say that the model was like, wait, maybe this is a moment where I should like change my reason or argument because it's not working. So I think they have gotten a lot better at this. But naturally, because of this one by one left to right autoregressive idea, potentially once they start making an error, this error would compound, and maybe with these discrete diffusions, this would not necessarily be the case. And then the last thing, which is again the thing that this Mercury model promotes a lot, is that potentially you can also have speed gains. So there has been a lot of work to make the transformers in the autoregressive setting as we use them today work quite fast. So there's been like KV cache, flash attention, which optimizes the specific kernel, all kinds of different innovations to attention to make it faster, not quadratic, but somehow cheaper. But at the same time, you're always limited by this idea that you can only generate a token T if you've generated everything that comes before it, and kind of one by one generated everything that comes before it. And as I showed you with discrete diffusions, we might be able to denoise bigger chunks at the same time. And that's why potentially you get these speed trade wins. Okay, so some pictures as to how these models would work for language, similar to how you would start with an image which is pure noise, and then kind of step by step denoise it. So some pixels get transformed into something that looks less and less and less like noise until you have Paris in the 1960s. It's sort of similar with diffusion models. So you would start with a sequence that is all masked or all random tokens, and then step by step kind of denoise a few tokens at the same time, where denoise means map them into tokens that are no longer noise, but actually make sense semantically, until in several steps you have your full sequence that hopefully makes sense and is an answer to whatever prompts you gave into the model. So again, visualization from Inception, because they have super many visualizations on their website. So here you kind of see that the model starts not with mask tokens, but with just random tokens that make no sense, Zap, Mango, Crisp, whatever. And then once you actually generate, once you denoise, you see that this turns into a sentence that then starts to make sense. Okay, another visual that sort of says the same idea as what I said. Okay, so to summarize, the promised benefits of why we should look beyond potentially autoregressive models. The first thing is speed. We will talk more on this, but you could potentially denoise multiple tokens at the same time so that we are moving away from this one-by-one slow kind of limiting thing. There's the accuracy, so maybe the fact that we allow to denoise in an arbitrary order might allow us to solve problems that are otherwise difficult with the autoregressive thing. So this A to B, B to A kind of relation, for example. And the last thing, which I took from a video that Stefano Ermon did on these diffusion models, is that you also have more axes of control, and that is maybe something that is generally nice. So you can change how exactly you noise your data, you can change how you're denoising the data, and playing around with these different axes of control might just lead you to better speed accuracy trade-offs, because again, you have more to play around with, more things to modify, and maybe you get to better things. Okay. If you want to read more on all of this, I know there's also a very nice talk right after on sort of this topic, but a few papers that I was reading are here. I won't go through all of them, but I think the first two are kind of like more fundamental and the latter two are more applications. All right, if everyone took a picture. Okay. So the things that I will discuss to explain how these diffusion models work, there's kind of 3 steps. So first we have a forward process, which is how do we go from clean, correct data to this noise data. Then we have to talk about the model and the loss that we use to represent and to optimize this. And then there's the backward process, which is at inference time, when I then give you a sequence of masked noisy tokens, how do you actually get back to text that would make sense? Okay, so this is the part where there is a lot of maths, not because I necessarily like maths, but because there's many papers that show you this math. So at the very least, if after this talk you're like, okay, let me read more on this, hopefully the ideas at the very least would look familiar and it wouldn't be this weird what they're all saying. And a lot of the maths somehow, I don't know, I think it complicates the main ideas, but whatever, we will go through it. So the forward process. So this is basically the idea of how do we go from a sequence to noise, because by doing this is how we will basically train our model. We are given like clean in quotation marks, internet data text, for example. We somehow need to teach the model to map this noise text to clean text. That's kind of like the main thing that we want the model to know how to do. And so we start with the sequence, and then we basically define like a forward process, which is how do we go from sequence to noise. And the idea is very simple. We basically say that we mask every token with a particular probability. In this case, beta t is the probability of choice. So basically every token in my sequence gets masked with a particular probability. And or if it doesn't get masked, it basically remains as is, the same as is. And I think, again, I'm stressing here this noise schedule. So how you exactly go from full sequence to masked is one of these elements that you can tweak. And potentially this is one of those things where by tweaking it, you might get some accuracy gains. Okay, I don't know actually how you guys feel about a lot of maths, because I can also skip like the next 3 slides unless you really desperately want to see matrix vector multiplications. Okay, I see some people want to see it. All right. Sorry for those that don't, but let's go through it a little bit. So you can be also a bit more formal. And the reason I mention this is, again, many papers on this topic, they would formalize it in this particular way. So they say, okay, this distribution that I just showed you, how do you go from cleaner data to less clean data? How do you noise it? It's defined as this categorical distribution where the matrix Q basically defines the probability of transitioning from some state I to some state J, where these states are basically the one-hot encodings of your tokens to some other one-hot encodings of the tokens. We can choose this matrix Q in many different ways. So you could choose it as some kind of like shuffling operation, which would mean you just shuffle your items in your vocabulary, like the one-hot encoding of your token. Or you can mask it with arbitrary tokens, or you could mask it with the mask tokens. And this is kind of the approach that I choose to do here. But I'm just saying that in principle, this is again a design choice. So you have the choice what kind of matrix Q are you choosing, which means how are you actually noising corrupting your sequence in this kind of like forward process. And so this was the math I was talking about. In my case, this is then the Q that I end up with, which basically says, okay, with probability 1 minus beta t, I stay as is. So the identity matrix, nothing changes in my 1-hot encoding of the token. And with probability beta t, I actually transition to this absorbing state, which is the mask. And as an example, suppose, for example, I have this 1-hot encoding 0100, which represents some particular token in my 4-token vocabulary. And with this choice of Q, then basically the distribution of the of the X after taking one noising step is equal or is distributed categorically with this vector, which is basically given by this. So it's exactly as I said in the very first slide, is with probability 1 minus beta t, we stay where we are, so the token that we had in this position. And with probability beta t, we actually move to the masked token, where here I assume that the masked token is represented by a 1 in the last position of my vector. Okay. We can generalize this by not masking it step by step. And I will show you why. During training, we basically want to sample random states t, and we want to know at this particular time t, how masked am I? So we want to have a distribution or a way of going directly from x0, our clean data, to some arbitrary xt. And if you do some maths, then basically this is what you would end up with, where the difference with the previous thing is that you just have this probability over these 1 minus beta t's instead of just the 1 minus beta t for a single step. And in simple terms, basically it says, if a token was never masked, so between 0 and t, it never got noised, then your xt is equal exactly to the x0 that you had at the start. And this happens with this probability alpha t. And if it was masked somewhere between 0 and t, then it's equal to the masked token, here denoted by m. And this happens with probability 1 minus alpha t. All right. So I'll get back to why I was going through all of that in a second. But then suppose that we have eventually our corrupted sequence. So in this case, I have corrupted x1, x2, x3, x4, x5, x6 into these masked positions in 2 locations. What you then do is very simple. You basically pass this through your transformer attention model. And as always, also with the autoregressive, you get out a bunch of probabilities, because that's just the last layer. That's how I define the last layer of this model. And these probabilities tell us, okay, what kind of distribution do we have over the elements in our vocabulary? So again, standard transformer probability outputs. But different from the regular transformer, where attention would be causal, which means that you only allow token I to see whatever happened before it. In this case, the attention would be non-causal. Why? Because you want this kind of like arbitrary ordering denoising. So whenever you're trying to see, okay, this masked token in this position, what would that be demasked into? You want to tell this guy what happened before it and also what happens after it. So the big change in terms of the architecture is that this attention thing is no longer causal. All right, and then how do we actually optimize what we optimize? So same idea as with the autoregressive models, we optimize this kind of log likelihood of how likely is the real token under this particular model. However, I only care about kind of learning properly what happened in this location and in this location, because I don't want to learn in the tokens that were already demasked. So I'm only computing my loss over these masked tokens. And if you've ever heard of this like BERT demasking objective, it is in principle very similar to that, because BERT has the task of, suppose I give you a corrupted sequence, the task in BERT is to then actually uncorrupt it. And this is very, very, very close to what we're doing here, except that I want to have a model that is able to model every step of the decorrupting process. So I'm not only interested in maybe, you know, a mapping from 3 corrupted tokens into 0 or 5 into 0. I'm actually interested in this complete backwards denoising process, which can happen with arbitrary kinds of numbers of masked tokens for arbitrary contexts around them. And that's why I do this training where the mapping is a bit more rich that we have to learn, if this makes sense. Okay, so a few more slides of math and then I stop. Basically, this loss function is, in my view, very intuitive, right? So I'm trying to learn this mapping from something a little bit noise to denoise, and I want this at different levels of possible noising levels. That's really all I'm trying to do, and I only care about optimizing it in the masked locations. But if you want to be more formal, you can, and you can actually derive the exact same loss function using this notion called the evidence lower bound, which is just a notion that is used in probability, and it formalizes this idea a little bit. So the way you would go about deriving it, and I'll be a little bit more quick, is that remember that this was eventually like this forward process that we had defined, right? So given a particular x0, I had defined a distribution over xt. So how does my noise sequence look given this particular x0? More generally, we can also derive it not just for x0, but any arbitrary s before t. Okay, we won't go through that math. And then using that expression, we can actually derive something that would help us structure the backwards process. So what we're interested in the backwards process is to know what could xs be with s earlier than t, given that this is my more noise state. So I'm going from more noise to less noise, and this would be the expression that you can derive for that. Okay. And why is this guy helpful? Why do I care about deriving this particular form of the Q of the less noisy one conditioned on the more noisy one? It's because this could inform for me what kind of probability I'm actually trying to learn. So I parameterize this probability distribution that goes into my loss function, like the thing that I actually want to optimize, by taking it in a very similar shape as this thing that we could derive analytically. Except since I don't actually know my x0, I parameterize that by this f, this f of xt. And that will be like the neural network that we're using in between. Okay, final slide with math. So the evidence lower bound basically has derives a bound on the probability of a particular x0, which is the thing that we want to maximize. This is then the whole bound. And then if you plug in this equation that I just gave you here into the term here, and you do some derivations, then basically you end up with something that looks like this. And that something is very close to exactly like the loss function that I had shown you before. So point being, if you want to be formal, if you want to walk through probability distributions and derive more formally what should my loss look like if this is my forward noising process, you can take these steps. You can derive your backwards probability, you can use this KL divergence evidence lower bound, and then you end up with something that intuitively makes obviously super much sense. You're just trying to optimize the likelihood of the true tokens x0 that we know during training, conditional on this more noise version, while sampling over different data points and different noising levels t. I wish you could ask me questions, but I guess you can only ask me at the very end, because I don't know if all of this makes too much sense, but okay, I hope it does. And I want to relate it back to also the autoregressive framework, because it is very close to what we were doing when we were optimizing these models in an autoregressive way, except here my probability is really restricted to be such that I can only learn, I can only model xi conditional on the exact path, and here I'm more free, I'm modeling xi conditional on the whole sequence, and here I care about every token, and here I only care about the tokens that I actually noise. Okay. Now things will be simpler because the general idea, I think, is very, very simple. So what we then actually do during training is we again take our huge corpus of texts that we're trying to optimize over. We sample batches of these texts. We then also sample different noise levels, which I control by t. Why different noise levels? Again, because in my final denoising, I want to be able to map any noise sequence to something that makes more sense. So I sample my t, and then I noise the tokens with this process that I had defined, which in my case was purely masking whichever random tokens I end up masking with my probability beta t. This guy I then pass through my language model, and I get out different kinds of probabilities that are attached to all of the tokens, and I'm interested mostly in the ones attached to the masked ones. Then I basically repeat this very, very, very many times, and this is my training loop. So I then take a new sequence, I mask again, maybe a different level of noise this time. I again pass it through my model. I compute these guys, I optimize with the loss function that I showed you, and blah, 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 I repeat this. And more precisely, if you look at one of the papers, this is kind of the algorithm that they define. So again, we take our data, we sample a noise level, we noise up to that level our original data, then we compute the loss by kind of maximizing the probabilities that are assigned to the true data given this noise one, take a gradient, run the optimizer, and repeat this very many times. Okay, now if you actually try to do this with diffusions, there are a few challenges with it in the sense that training a diffusion model is a lot more noisy than training your regular autoregressive model. Why is this the case? Because you have to imagine that in every iteration, you're not just showing it different samples of the data, but you're also showing it samples that are exposed to a different level of noise. So between your batches, quite a lot of things can vary. So whatever gradients you kind of like optimize on batch 1 might have a very different direction in batch number 2, because again, I'm noising at a different level. There's a lot of my sample is different. There's a lot of things that are more noisy compared to a regular autoregressive model. And that's why if you look at the curves here, I took the curve from the paper block diffusion, you really see that's the brown line, the diffusion does show a lot more noise than the autoregressive one. And yes, that can be a challenge at times. I was trying to convert a pre-trained autoregressive model into a diffusion one, and it was really hard to get rid of the noise, so to basically have it actually like optimize into something sensible, because the optimization task is frankly not that easy. I'm asking the model to learn to map arbitrary noisings of big sequences of text into clean ones, but arbitrary noisings, so there's very many different combinations that I'm asking the model to learn. Okay, so anyways, suppose you have managed to do your training. What would inference look like? What would this denoising process look like for these discrete diffusions? I think I alluded to it already many times, but we start with a fully masked sequence. We pass all of this through the language model, and we get out very many probability distributions for all of these masked tokens. But what we do, we could accept all of these tokens in one go. So we could sort of denoise in a single step and just say, okay, everything that came out here is correct, fine, let's go. This won't lead to very good accuracy most of the time. So that's why people say, okay, let's actually accept some tokens. And I will say how to define how we accept them in a bit. So let's say we accept x2 and x5 because we think, okay, they had a good confident prediction. Then we pass again, but this time with already x2 and x5 denoise. Then we look at the probabilities assigned to the still noisy ones, and we basically do the same. We accept a few, and then finally we have like a full sequence. And this is also where this potential speed up comes from, because again, I can accept multiple tokens in one go. If I have a very good diffusion model, then potentially, hopefully, I can actually accept maybe, for example, 2 tokens instead of a single one that would be the case with the autoregressive one. So yes, this is basically what I just said, this promise of speed. Since we're not limited to left to right one by one generation, but we can actually unmask multiple at the same time, that's where we get potential noise speedups from. The other thing to say is that all of this is really a generalization of autoregression, because what if I restrict my denoising schedule to be such that I only accept a particular token when the pass has already happened? Then I'm basically back at autoregression. So there's this paper, You're Absorbing Discrete Diffusion Secretly Models the Conditional Distributions of Clean Data. But everything that this paper says is that masking tokens randomly and predicting them is approximately equal to training over all possible generation orders, autoregressive being a subset of that. So as I said before, this notion of like which tokens do I accept, they can really play with your accuracy. So the generation quality really depends on how do you decide to accept certain tokens and which ones do you still keep masked. And there's kind of obvious ways we can do it. So we could, for example, just say, okay, we look at the probability distributions that the model gives us. We either sample greedily or stochastically, similar as in regular autoregressive models, and we say, okay, let's just randomly pick k tokens. K can be 3 because I like 3, and let's accept these, and then we kind of repeat in this way. So then the speed up that you get is kind of related to this, how many less you have to do for the full sequence because you're taking steps of k. You can also do more clever things. You could say, okay, I'm actually going to look at how confident my model is in this particular token, and I'm going to accept the tokens on which it is the most confident. So let's say I accept the 3 most confident tokens or the 3 lowest entropy tokens, so slightly different but related ideas. Or you can say, okay, I only ever accept if the confidence is above a certain level. So then you're kind of like generating until the model is sufficiently confident. This confidence defined by your threshold of choice tau. And for example, to show the order that the model ends up deciding, here the prompt is, okay, Lily can run 12 kilometers per hour for 4 hours. After that, blah, blah, how many kilometers can she run in 8 hours? And if you look at this diffusion model LADA, the light colors are those that have very high confidence, so that are demasked very early on, and the dark colors are actually demasked much later. So you see that the model doesn't end up choosing an autoregressive schedule. It starts with demasking, for example, this like 8 hours here, so somehow it already knows that is something that it should use. Lily is also demasked very early on because, okay, maybe the main person in this question is Lily. But so you see that the order is really not purely autoregressive, and maybe again this could then hint that autoregressive demasking could have been potentially suboptimal because maybe denoising in this random order is better. As I already showed early on as well, the performance of these discrete diffusions sort of began to match autoregressive models quite recently. So this is Mercury, their coding model, and they compare it to other models, and they basically say, okay, at a much higher speed of generating tokens, we are actually getting similar accuracy to these Claude 3.5 Haiku, which by now is maybe a bit old, but sort of progress is happening. And if you look at the papers, similar things. For example, this LADA 8 billion, which is a diffusion model. On certain benchmarks, as you see, clearly not on all of them, because the Llama autoregressive model still outperforms on many others this guy. But on a few benchmarks, the performance is getting close. But at the same time, if you then do a kind of literature search over what have been the most recent directions that people are taking with these diffusion models, for example, LADA, the original 8B, then said, okay, let's scale up this model to 100 billion parameters. And in a way there, the argument was maybe the reason that diffusion models are not performing as great as autoregressive is because so much work has gone into autoregressive. So many people have trained these in big sizes. And maybe the reason diffusions lag behind is purely like the size question. So they were like, okay, let's scale it up to 100B and see what we get. However, what they actually ended up doing as well is that they started out with this autoregressive model. So they took a pre-trained autoregressive one and then ended up turning it into a diffusion model by slowly changing the training objective to be this kind of arbitrary masking thing instead of the autoregressive one. So yes, they managed to train it. Yes, they sort of match performance, in this case, to the Qwen 30B model, which is nice. But at the same time, they really did leverage the work done by the autoregressive modeling approach. Also, there are limitations. So this thing that I just told you early on, which is this idea that we can arbitrarily decode in different orders multiple tokens at the same time, can actually also be a challenge with these models. So here, for example, they ask a prompt, pick a random city for travel, New York, New Orleans, Mexico City, or Panama City, and they denoise 2 tokens at the same time. And so the model ends up generating new city, which doesn't make sense. But why does this happen? Because this guy, when he's being generated, he doesn't know what this guy said, and this guy doesn't know what this guy said. So they assume independence, but they're actually, in this case, they shouldn't be independent. So you might make these kinds of mistakes because of this arbitrary and multiple token at a time denoising. So for this to work, I guess you would hope that your model learns which tokens are actually independent and only denoises those at the same time. But again, that's kind of like a learning problem. I also had this whole story about diffusions are nice because they allow you to self-correct maybe more reliably because we're demasking in different orders. So maybe it can more reliably fix mistakes that it made. But if you again look at recent literature and what they're actually doing, there was this LADA 2.1 now paper that said, okay, we might be still demasking in the wrong way. So let's actually also allow for an operation that is this, which basically says if a token has already been demasked, before we used to keep it fixed, but now we actually say, okay, if the new argmax, so the new most likely token after passing in a bit more denoise sequence changes and the confidence is high, we also actually again allow to change the token. So there, in a way, the original demasking wasn't enough and they have to add another kind of demasking on top to maybe fix the issues that happened, for example, with this new city kind of approach. So not too great because you're adding more, potentially more sampling steps onto your forward process. And that was the whole benefit, that maybe we didn't need as many forward steps. Okay, another paper that was called Introspective Diffusion Language Models, blah, blah, blah. Essentially what they then said is, let's actually also remove the non-causal attention and let's also predict, instead of predicting the mask, having the mask token predict the current token in the same position, let's have it predict the next token. And then we're again kind of closer to the standard things we use in autoregressive models. So why am I showing all of this? I think there was this big potential of these diffusion models and people were very excited. And I still think Inception and Mercury have done a great job at a lot of things. But if at least we look at the open source models and the research papers people are publishing, diffusions still really lag behind. And attempts to scale them up, so to really improve their performance, they really leverage a lot of these pre-trained autoregressive models. They allow for token editing, so potentially again slowing down inference. They go back to causal attention and so forth. So for me, after doing this kind of like review of everything happening, I think the verdict is still a bit out on which model will actually be the best, or whether all of this will somehow converge into a single unified approach. And the reason I say this is if for example, you look also at recent closed models, sometimes you see them kind of like denoising many tokens at a time in kind of blocks. So there was this paper, block diffusion, that kind of leverages the best of both worlds. Maybe we still do autoregressive a little bit, but we still denoise in little areas in this discrete denoising way. Okay, that's it.
Great. Thank you very much for your nice talk and not being afraid to show some vector multiplication. I think this is directly the right audience. Yeah, now it's time for questions. So is there anything you would like to ask?
So how do we manage generation length in this case, since when we have, of course, autoregressive models, we generate the end of the sequence token, but here, how does it work, basically?
So I don't know the state of the art approaches in the sense that I'm sure they must have some clever ways to not start with like arbitrarily way too long sequences. But when I use them, and I'm currently using them for finance, so for time series modeling, I do just fix a sequence length. So I'm saying like, look, I'm interested to predict 10 time steps ahead. This is what I'm fixing, and that's the one that I'm then denoising. But I'm sure there are more clever tricks as well to do, but it's a good question. The simplest answer is we fix the sequence length a priori.
So you had in the beginning this very nice example, starting from like random words, you converge to an answer. Now, what if I start with a good answer, except I delete one word? This seems like we're very close, but seems hard for this model to fix. So what would happen in that case?
So I think that should work. So that is kind of like this BERT demasking approach, where they would say, okay, my sequence is not completely corrupted, but maybe it's corrupted in a few places. What would be the right uncorrupted thing? And also when I was trying to turn these autoregressive models into these discrete diffusion models, if you instantly give it the task of like, okay, here is your 100 length sequence, my T that I sample is like high, so 90%, for example, gets masked, good luck, denoise it, you will never converge because my loss just gets stuck high. But if I make the task simpler, so I actually only start with a very small amount and potentially something at the very end of the sequence to keep it closer to the objective that the autoregressive one was optimized for, that works well. And then slowly you kind of expand this. So to answer your question, I think a few is actually easier to potentially do.
Hello.
Hi.
You mentioned both the advantages and disadvantages of the diffusion and autoregressive models. So how would be a hybrid approach to like, is it something studied or what do you think?
Yep. So I think probably, wait, if I have it here. Yes, I think this one is actually like the hybrid approach that people use, block diffusion. So the idea being that we don't assume diffusion over the whole sequence, but only in blocks. So the blocks remain causal to each other. So I only generate block 2 when I've done generating block 1. But inside block 1, I do my diffusion objective. And then you sort of get this best of both worlds. Yeah. And I think that's also what I wanted to say at the very end. People are converging to a lot of hybrids of all kinds of different architectures. So partly hybrids with diffusions, partly hybrids with state space models. So in a way, all of this might end up to be like one kind of like big architectural framework.
Do you hear me? Okay, great. Thanks for the talk and the great introduction. I was just getting curious if those models learn strategies, so they would only focus on a few tokens, because I can like imagine maybe like the internal representations would be in better use if they would only focus for certain word predictions, right? So maybe there's like a lot of overhead in each steps. Are those models learning strategies to focus on certain outputs so that their internal representations already would like focus on this specific task? Yeah, do you get it?
You're saying to kind of like explore where attention is going in terms of this the sequence, like this, or?
Yes, exactly. So that
Yes.
if the model knows I want to output this thing, then maybe it's sensible to have different attention than otherwise.
So I have actually not looked at that for diffusion models, but it would be interesting from an interpretability point of view to look where the attention actually goes when we change the generation order. So yeah, but I don't know, but it's a good point.
Okay, thanks.
Hello. Last year's reasoning models, they took the lead, right? Let's say in LLM space. And what about diffusion models? Are they capable of such complex reasoning, or like when you have this constraint, let's say generation of group of tokens, right? Like would it be kind of opposed to this unconstrained reasoning?
Yeah. So again, I don't necessarily know, but I think sometimes if you read the reasoning chains of the big autoregressive models, like I read it when Claude generates me something and it makes like absolutely no sense, and it sort of goes back and forth between weird things. And there's actually a lot of people that are also claiming that these reasoning chains should not be interpretable. We should not think that they are interpretable because maybe they are not. Maybe the model is still kind of reasoning in some latent space and only the final answer is what we should look at. But in any case, what I'm trying to say is that you see the reasoning chains going into like, I don't know, it takes sometimes very many tokens. It goes into like arbitrary directions. So I would have hoped that diffusion models sort of are better at this because of maybe indeed this re-editing or these different generation orders. But I guess so far we haven't really seen it because, okay, we will see what Inception comes up with and maybe they launch a model tomorrow that is better than anything out there today. But right now I think the main things are still just the autoregressive regular ones. Maybe again because we've put so much compute and attention to them. So yeah, yes.
Actually, I was asked the question, but maybe that the expansion of the. If you think about like reasoning is bad.
So just an extension on this question, like I assume reasoning is truly like on a longer time scale, it really has to be causal. No, like you cannot come up with a token at the millionth position unless something really happened before. So So I wonder, so my intuition is that this diffusion must have a limit in terms of length that is reasonably you can generate at the same time.
Yes, so I agree. That makes a lot of sense. I'm trying to remember the exact discussion that those people that were working on this were telling me. I guess they were saying something like this. So maybe in my head, before I start speaking to you, I have already formed that I want to end up at this thought here. And maybe in between, I enter this thought here. And only then do I start filling in all of the things that I'm telling you now. So I think their argument was that maybe reasoning is not necessarily purely causal, because you might want to, but yeah, I agree with you as well. Like, I don't know what I'm going to say even like in a minute from now. So there is definitely a limit to it. And that could also be why these models are not yet outperforming, because actually, step by step is sort of better. Or it's also the wrong granularity, because here I'm allowing for tokens at arbitrary orders. But what I just explained to you is in terms of ideas at arbitrary orders. So kind of, differences in the latents. But
so I had a question regarding token diversity. Is it, given that the whole process of learning the dependencies between arbitrary positions is more complex, do these diffusion models tend to collapse more to the same kinds of thing? Because in autoregressive LLMs, we try to generate a lot of new synthetic data and all these kind of things. I could see that being a problem with diffusion. What do you?
You think the collapse to be a problem?
No, as in more calibrated. Calibration can be worse in diffusion models, like overconfident predictions.
Right. Well, okay. Again, I will start with I am not sure, but in my domain now in finance, there was actually a hope that they would be more regularizing, because I'm forcing it to map from different noise levels. The mapping problem is more complicated. I'm not just asking like this sequence, the next guy. I'm asking this sequence masked here, but also masked here, like different kinds of mappings that I want to learn. So they were applying it to finance from this perspective of maybe actually it has a regularizing effect and the very noisy finance data is overfit less. I can come back to you in a year, because I don't yet know if this actually is going to work. We're trying it in a way now as well, yeah.
Thanks. I wanted to ask if your inspiration was denoising image generation. How did you come up with accepting tokens so early? Because in image generation, everything stays like unsure of until the very end. But here you're accepting, that would be like accepting pixels in the first run.
Yes.
And keeping them till the end. How did you come up with that, and why?
So it's not me. It's one of these papers that came up with this. And I think indeed like this approach at the very end that I showed you, I won't scroll through the slides again, but this one where they allowed for additional editing of already sort of denoised accepted tokens. They maybe do more like images that the pixel can change up until the very end. Maybe also the next talk, by the way, will touch upon this. Yes, okay. But potentially it's just like an easier modeling choice, that by fixing them, you don't have to pay attention to them anymore. And then you can at least get some better understanding of like the speed ups in terms of the denoising. And also, by the way, I should say, so when I was doing also this literature study, it seemed like this paper is from like super long ago, or like in ML terms, super long ago. And it took a while for people to make them work on language. So there seemed to be just like also computational challenges. So maybe that is also a reason that this kind of stuff, these decisions were made at some point. But we are revisiting them now, because maybe they were indeed not the actual optimal ones.
I have a question from your slides. Could you please go to your backward process slide?
Yeah. Oh, a math question.
No, really.
This one?
The one just before the diffusion slide. I don't remember now, but this one. Yeah.
Okay.
So this DKL, is that the so-called the effective diffusion coefficient? And this process?
This guy?
Yeah.
It's like the KL divergence.
Okay.
Which is like the distance metric for probability distributions.
Okay.
And
I was just curious, because this is a so-called diffusion process that's happening. So there should be an effective diffusion coefficient or effectively a time scale, a schedule that usually, like in mathematical physical systems, separates two, like a local and global structure formation. So it separates two like time scales where local structures forms vs global structures. And I was just curious if this, in this context, does some parameter like your diffusion coefficient, whatever, control like how early structures form, I don't know, maybe grammar, basic grammar versus like meaning, which is a complicated, more advanced structure to form?
Okay, this I don't know. I think that's an interesting question in terms of these like structures. But at the very least, like, so in this equation, we how do I say? This is indeed like a stochastic differential equation in a way, except that again, it's not in continuous time, but there is a certain noise term, and the magnitude of this noise term and the location is controlled by this kind of beta t parameter. There's not really maybe a drift term per se, but so yes, it is very much related. And I do think what you're saying, again, maybe next talk, but I do think people look into this. There are people that are studying these processes from a much more theoretical, mathematical, physical way. One of my collaborators does. He's much better at this than me. So I think there would be literature for you to look into. But yeah.
Yeah, I guess probably in the continuous diffusion field.
Yeah, maybe, yes.